Right, so I just wanted to briefly cover what the mole is and how we use it, and a couple of different calculations of how we can find the number of mole from the number of particles of something that we have, and also the number of particles of something based on the number of mole. So you've probably covered this before, but the mole is really just a really big number. So you can have a mole of anything, and it just means you have 6.023 times 10 to the 23 of that thing. So you can have a mole of books, have a mole of chairs, you can have a mole of tables, whatever. It just means that you have 6.023 times 10 to the 23 tables or something like that. So obviously the reason you don't use that in everyday life is because no one has that much of anything. So it wouldn't be useful. So the reason we use it in chemistry is because there are just so many molecules. In a glass of water, you've got 18 grams there, you have 1 mole of water. So you have 6.023 times 10 to the 23 molecules of water. And that's really annoying to say. You can see that I'm already getting frustrated having to say the number over and over again. So rather than counting to 6.023 times 10 to the 23 every single time, I'm talking about a number of molecules. Instead, I can say that I have 1 mole of water in that glass, for example. So the majority of the calculations we do in chemistry use moles rather than the number of molecules. And in particular for your IGCSE exams and things relating to that, the only time you're really going to be talking about the number of particles is if an exam question directly says how many molecules or how many particles or how many atoms are there in this thing. And for this, I'm going to go over basically 2 different types of calculations that you can come across. So I'm going to be doing this in 2 different ways for each problem. So I'm going to be doing it using cross proportion, which is an easier way to do it and a better way to think about it, but it will be a bit slower in comparison to the equation way of doing it, which, if you remember the equation and you can understand it, is a faster way of doing it, but it does mean you need to have that understanding there, remember what the equation is, and know how to implement it. So I've put the example question from my notes here on the slide. So I have a question of a sample contains 2.7 times 10 to 24 molecules of methane. How many moles of hydrogen are in the sample? So regardless of what the question asks, if it's numerical, both in chemistry, physics, and maths, I always like to lay out all of the information that I have right at the start. So I'm going to write here on the side that the number of CH4 molecules is equal to 2.7 times 10 to the 24 molecules. And what other information do I have? I know that Avogadro's constant is equal to 6.023 times 10 to the 23. So any question that has a number of molecules there or asks you about a number of molecules is probably going to need Avogadro's constant. And Avogadro's constant is in molecules per mole. And things that we don't know are the mole of methane and the mole of hydrogen. All right, so if we're doing the cross proportion to find the answer, the first thing that we always do is set up a 2 by 2 grid. And we're going to have one ratio where we know both sides of it. We're going to have one ratio that has unknown information compared with a known value. So on the top, I'm going to say, yes, my pen starts working, 6.023 times 10 to the 23 molecules are in 1 mole. I know that because that's just what Avogadro's constant is. Every time I have 1 mole of anything, in this case methane, I would have 6.023 times 10 to the 23 molecules there. And down the bottom here, I'm going to put the number of molecules in the sample, which is 2.7 times 10 to the power of 24. But I don't know the mole here yet. So I'm going to put N methane. All right. And there's a few different ways we can do this using maths. So you can do a cross product where you multiply those and set it equal to those. The other way that you can do it is you can say this divided by this equals this divided by this, or vice versa. So if I do that and put that over here, I have N divided by 1 is equal to 2.7 times 10 to the 24 over 6.023 times 10 to the 23. And that's around about equal to 4.5 mole. And always make sure you write down what you're finding. So I've got the amount of methane here. So I haven't actually completely answered the question yet, because the question has asked how many moles of hydrogen as opposed to moles of methane. So for this, I'm going to remember that it's 4.5 mole. I'm going to do another cross proportion. I'm going to say that for every 1 mole of methane, I don't know why my computer's doing that, I have 4 mole of hydrogen. In the same way, if I have 4.5 mole of methane, then I have N mole of hydrogen. So doing this divided by this and this divided by this, I get N over 4 equals 4.5 over 1. And if we do maths on that, we get 18 mole. And I'll write that down as the mole of hydrogen. And this is our final answer. So you can see it took a few steps, but hopefully this idea of ratios makes sense. And you can basically solve these ratios in whichever way you want, as long as you're not dividing mole by, like the mole here by the mole here or something like that. All right, so the second way I'm going to go over doing this is much faster, and that's often the way that's covered in textbooks, and it's just this idea of an equation of number of mole equals number of particles divided by Avogadro's constant. And we know N equals 2.7 times 10 to the 24, Na equals 6.023 times 10 to the 23. Therefore, this equals 2.7 times 10 to the 24 over 6.023 times 10 to the 23, which is around about equal to 4.5 mole. And then from that, I can say I know the amount of hydrogen is equal to the amount of methane times 4, which is equal to 4.5 times 4, which is equal to 18 mole, which gives us the same answer as the previous way of doing it. And you can see it's a bit shorter, but right at the start, you need to know that this equation was there. Just a note as well, if you're going to use the equation, don't just make it suddenly appear like this with all the variables in it. Write out the whole equation first without having subbed in any of these variables, just so the examiner knows exactly what you're doing. And it means if you completely stuff up the rest of the question, you'll often still get a mark just for saying in the equation. All right, so you should be able to do the reverse calculation as well. So in here, I've told you an amount of mole of methane and asked how many molecules of methane are in the sample. So again, I'm going to write out my information. I've got 0.57 mole of methane. The number of particles, I don't know. And Avogadro's constant, I do know. Molecules per mole. If I set up a cross proportion for this, again, I can say that there are 6.023 times 10 to the 23 molecules per 1 mole. And then I can say that there's N molecules in 0.57 mole of methane. So then if I do the ratios here, I get N over 6.023 times 10 to the 23 equals 0.57. So N is going to be equal to some number that I didn't calculate. So 0.57 times 6.023 times 10 to the 23 is 3.4 times 10 to the 23. And that is molecules of methane. So obviously if I'd ask for hydrogen, you'd have to do an extra multiplication there. And then we can do the same calculation using an equation like this. Again, we know N equals 0.57 mole. N is unknown. And A equals 6.023 times 10 to the 23 molecules per mole. We sub these into the equation. 0.57 equals N over 6.023 times 10 to the 23. Therefore, N equals 0.57 times 6.023 times 10 to the 23. And that'll give us the same as the last page, so 3.4 times 10 to the 23. All right, and that's molecules CH4. So hopefully from these examples you can see what I'm getting at, and you should be able to apply these different calculations to whatever's in your textbook or whatever questions have been given to you. All right, so next I'm going to be going over conversions between masses and molar masses and amount of mole, but that'll be in the next video.